The next unit that we're going to take a look at will be curve sketching and optimization. Up till this point, we've developed a variety of techniques in order to take the derivative of most functions that we would encounter. We now want to extend those ideas to patch up some holes in the curve sketching algorithm that we learned in advanced functions. Namely, the first problem with our curve sketching algorithm from advanced functions is we had no way of determining exactly where these local maximum and minimum points occurred. The first derivative test will allow us to figure that out. If we plot our original function f of x here in black on the same axes as its derivative f prime of x, we can glean a few pieces of information that we may or may not have already known. We'll see here that anywhere f of x has a tangent that is positive or increasing, f prime of x is also positive. Anywhere that f of x has a tangent that's decreasing or a negative slope, we see that f prime of x is also negative. We can also gain one final piece of information here, is that anywhere we have a local maximum or minimum, we also have a horizontal tangent, or a slope of 0. This corresponds to roots of f prime of x. So algebraically, we can determine this by first calculating the derivative as normal, setting it equal to 0, and then finding these points. The next piece of information that we can find is we can now determine exactly where f of x is increasing and where it's decreasing. In order to do this, once we already have the roots of f of x, we can plot them on a number line and check points between and around these roots. In order to do this, we will pick a point less than the smallest root, a point between each of the roots, and a point to the right of the largest root, and check the value that appears when we sub them into the derivative. If that result is positive, then we expect on that interval f of x will be increasing. If that result is negative, we expect f of x to be decreasing. Similar to the first derivative test, we can take the derivative again. By doing so, we can determine points of inflection. Points of inflection are points where f of x changes concavity. Well, what is concavity? Concavity is a way of measuring whether or not f of x is opening up or down. By this we mean if the graph is curving upwards, we say this is concave up, and if it's opening downwards, we say this is concave down. Any points where f double prime, or the second derivative, is equal to 0, these will be inflection points. Inflection points are where the graph is changing from concave up to concave down. If you notice here, on the left-hand side of the graph, it clearly looks like f of x is opening down, and on the right-hand side, it looks clearly like f of x is opening up. Somewhere in the middle here is a point where it changes. This will be where f double prime of x equals 0. So by setting the second derivative equal to 0 and finding its roots, we can now determine any of these points on the original function. In addition, similar to the first derivative test where we figured out intervals of increase and decrease, we can now figure out intervals of concavity. In the same way that we did before, plotting our roots of the second derivative on a number line, and testing points to the left and the right and in between, we can find anywhere that f double prime of x is greater than 0, then the graph will be concave up. Anywhere that the second derivative is less than 0 will give us points where f of x is concave down. Next, let's take a look at an example of how we can apply the complete curve sketching algorithm. We're going to have a 5-step algorithm. First, we're going to determine any asymptotes, find all x and y intercepts, we're going to use the first derivative test, we're going to apply the second derivative test, and finally, we're going to graph. If you haven't already, review all your curve sketching techniques from advanced functions. You should be comfortable finding all vertical, horizontal, oblique asymptotes, as well as applying synthetic division and using the rational zero theorem. So let's run through this specific example. The example that we're going to look at is graphing 1/3 x cubed plus x squared plus x. So the first step in our algorithm says, let's determine any asymptotes. Obviously, this is a cubic function, and thus it's not going to have any asymptotes. The next step is let's determine any x and y intercepts. We know that normally we would apply the rational zero theorem, and then use synthetic division to determine roots. In this case, when we factor this function, we see that we end up with a common factor of x and this quadratic. If we check this quadratic, we'll determine that there are no other roots. Thus, when we solve for x, we end up with only x equals 0. Subbing x equals 0 back into f of x will tell us that 0, 0 is both an x-intercept as well as our y-intercept. The next step in our process will be to take the first derivative. So let's take the derivative of this function. At this point, we should be pretty comfortable of taking derivative of these type of things, as this is a polynomial and we've done this since Unit 1. So we end up with a quadratic function, x squared plus 2x plus 1. As we already talked about, the first derivative test involves setting the f prime of x equal to 0 and finding its roots. Well, factoring this function, we end up with a double root, x plus 1 squared, and giving us a root of x equals minus 1. If we do a quick sketch of this derivative, we'll see that f prime of x is always positive. This tells us that according to the first derivative test, f of x should always be increasing, and that will be reflected in the graph that we draw. Next, let's apply the second derivative test. So taking the derivative of f prime of x, we'll determine f double prime of x is going to be 2x plus 2. Again, setting this equal to 0 will determine any roots of the second derivative. We end up with only one, x equals minus 1. Giving a quick sketch of this graph, we'll see that it's going to be positive to the right of minus 1 and negative to the left. This tells us that we should expect the graph to be concave up on the right of this point minus 1, and it should be concave down on the left. If we want to know where this inflection point is, we now know the x value at which it occurs, but we don't know the y. So subbing this inflection, this critical point, back into f of x will tell us the y value that it corresponds to. We can also take the critical point that we derived from the first derivative test and determine whether or not this is going to be a local max or min. We would expect that if this was going to be a local max, then the graph should be concave down at this point. If it was going to be a local min, we would expect it to be concave up. In order to do this, let's take this value and sub it into the second derivative. If we get a positive value, we would expect that the graph is concave up and it's a minimum. And if we sub it in, we get a negative value, that would tell us that it's concave down and a maximum. In this case, we get f double prime of x equals 0, which makes sense as we determine that this is both a critical point and an inflection point. Thus, this is neither a max or min. The final step in our graphing algorithm will be just to graph. So let's take all the information that we've gathered in these 5 steps and graph them on our axes. So we can place any roots, asymptotes that we have, and then use the information about when the graph is increasing and when it's concave up and down. So we'll notice here that, as we suspected, the graph is always increasing, as well as it's concave down to the left of this point, minus 1, 1/3, and it's concave up to the right. We'll see many more examples of how to apply this in our homework. Good luck.